Good evening. Welcome to video 1 of topic 1 of unit 4, electromagnetism. Now, unfortunately, my digital pen has sort of hit the bucket, so all the math in this will be done using typed stuff. I do prefer to write it and show you how to work it. However, I felt it was better to have the video out rather than not having it at all, so we'll make do, unfortunately, until I can get a new one. So this video will be looking at the main ideas of chapter 6.1 of book 2. Note all of unit 3 used book 1, most of unit 4 is going to use book 2, and a little bit of book 1 when we do light towards the end of the year. So we're going to start with Coulomb's law. Here's our learning intention and success criteria. Have a read and complete the KS table down the bottom right there. Okay, so having a look at the learning intention there, you should be able to use Coulomb's law to calculate the force acting on a charged particle. That's the main goal here. So some things you should be able to do: explain the relationships inside Coulomb's law. If you understand the relationships, then using the law will be easier. I want you to be able to calculate the electrostatic force acting on a particle, and then look at doing the net force for multiple particle situations, both in 1 dimension and 2 dimensions. So for the year 11s, that will be a little bit new this year. So having a look through our KS here, well, if we don't know what Coulomb's law is, we won't know how to use it, so we need to know what it is. And we need to know what these relationships are. In terms of skills, well, firstly you've got to calculate that force, and then how do you do calculations of forces in 1 dimension and 2 dimension? Okay, so the first part of our topic of electromagnetism is electrostatics. And if you break down the word, it makes sense in that we're looking at objects with electric charge, okay, electricity, anything with a charge, and static, in this case, means stationary position. So we're not dealing with anything moving. So these first few videos are going to look at the nature of electric charge, and we learnt about charged particles in Unit 3 when we did electric circuits. So let's recap a few important points that we need to know. The first is that charges can come as positives or negatives. If the charges are alike, they're going to push against each other. If they are opposites, they will pull against each other. Our second thing is that a negative object, okay, so anything negatively charged, has extra electrons on it, while a positive one has lost some electrons. Charge, we give the symbol Q. I generally prefer the symbol lowercase q. We're going to see the syllabus wants us to use a capital and a lowercase, which is a little bit annoying, but we just have to make do. And the unit for charge is the Coulomb, given the symbol C. Now, the smallest possible charge we can get is the fundamental charge on an electron. Q equals 1.6 times 10 to the power of negative 19. Now, this value as fundamental charge is provided in the physics booklet, all the equations and the constants. So you don't need to memorize this number, but you need to memorize that it is a number, then you know where to look it up. Being as though you're going to do a fair amount of stuff involving this number, it could be worthwhile just to store it for your memory, just to get through your exam, just to speed things up. So we've said here that forces can push and pull, so there must be a force here. Okay, so if we're pushing and pulling, there must be a force of some sort. Now, in 1885, there was a French physicist by the name of Coulomb, and you should try to put a bit of accent on it because it's French, and he did a lot of work on electrostatics. Now, we already knew before then that things pushed and pulled, but we didn't know the math behind it. And he got what's called a torsion meter, a very sensitive one, and torsion is basically how much force of twisting is on it. You may have heard the word torque before. And he found a few things out. Okay, we repeated his experiment this week in class using that PhET simulation. I don't have a torsion meter. Now, he found a few things, and we found the same thing in our pracs. He found that as either charge is increased, the force increases linearly. Okay, so if we let Q2 equal 1, and we just increase Q1, it goes up in a linear value. If we increase both at the same time, again it will go up in a straight line. Okay, so force is directly proportional to Q. If we increase the distance between our charges, however, the graph is a inverse curve. I do think this one's a little bit weird in that this seems to overhang just a slight amount. However, we found that it was related to the inverse of the square of the distance, not just the inverse of the distance, the inverse of the square. And so Coulomb formed his law. Let's bugger. We have here that the force, okay, and I like to use F subscript E. The syllabus doesn't. They just go force. I like to put the little subscripts with it so I know which force I'm referring to, but you're going to have to be aware of that. Force subscript E equals 1 over 4 pi epsilon naught times the product of the two charges, capital Q and little q, over r squared. This here at the top is how it will look in your formula booklet. Okay, if you take on some of my habits and do things like let's put the E there, or instead of writing this 1 over 4 pi epsilon naught, I do K with a subscript C for Coulomb's constant, that's not a problem. However, you may as well just do it the way that the syllabus does. So let's go through what these things mean. F is force, it's in newtons, like all our other forces. Big Q is one of the charges, little q is the other charge. And it doesn't matter which you do, because if you multiply A times B, you get the same answer as if you did B times A. So I don't know why they've done two separate Qs. And R is the distance between the two in meters, and I try to remember it as R as in radius, that way we're thinking about the distance. Now, because charge can be positive or negative, if we put those negative values into our formula, we could get a negative force. So we need to know what they mean. This textbook tells you to get rid of it and just think about your context clues. I personally like to use it because it tells you what the answer should be, and it gives you an extra reminder. Okay, if your force ends up being positive and we put two positive charges in, or we put two negative charges in, well, we know if we multiply two positives, we get a positive. We multiply two negatives, we get a positive. And so if our force is positive, then our force between the two charges must be a push. Same signs, push. Same signs on on numbers, push. Same signs end up being positive, so positive is the push. Okay? But if one of your charges is negative and the other is positive, and you multiply them together, you're going to get a negative number. And so if your force is negative, that means that it's a pull or an attraction between the two charged particles. Now, this constant at the front, this 1 over 4 pi E naught epsilon naught, that's looking very complicated there. The way it is written in the formula booklet is sort of like here. 1 over 4 pi epsilon naught equals 9 times 10 to the negative 9. You're not expected to use this epsilon naught anywhere else. The value is called the permittivity of free space, and it refers to how easy it is for electrical charge to sort of build up between two places in a vacuum. It's completely outside the scope of our syllabus. I don't know why they've done it like this. You do see it like this a lot more at university. I personally just think it's their aggravating way of doing it, instead of just doing a value of K for some constant, which would have made a lot more sense to me. Okay, so let's head on to some examples on this. We've got 5 examples. Here's example 6.1a, and we have here, there are system of two charges, as shown in the figure. We have capital Q equals plus 10 microcoulombs. Note the U with a little tail there for microcoulombs. And little q equals negative 5 microcoulombs, and the separation distance is 30 centimeters. Calculate the force between the two. Okay, so we're just going to get straight into using the formula. Let's identify our variables, first. So capital Q, 10 times 10 to the negative 6. Little q, negative 5 times 10 to the negative 6. Walding doesn't like doing the negatives for it. I do, so feel free to have a look at his working out. And if his makes it easier for you, feel free to follow his working out. I would not penalise you for not doing it, but there is a step coming up that it's important to keep it in mind to do. And you can either do it by using the math, or you can do it by using your context clues about the information provided to you. We have our radius. You could write it as 0.3 metres. I've just converted centi straight into power notation. You'll get the same answer. And our force, our electric force, is unknown. That's what we're trying to work out. So let's chuck out our equation. Okay, force electric equals 1 over bleh, QQ over R2. Let's do our substitutions. 9 times 10 to the negative 9 equals, and here we can see our Q1, or our big Q, 10 times 10 to the negative 6, our little q, negative 5 times 10 to the negative 6, and our radius squared on the bottom. I am doing it like this, just to sort of give you a bit of idea, because a lot of the examples just use centimetres in this text. But if you're dealing with weird distances like nanometers or picometers, you're probably going to end up using decimal notation times 10 to the power of whatever, some small negative number. And it's important to make sure you do this right, because if you do just 10 to the negative 2 squared and you get just 30 times 10 to the power of negative 4, that's not the right answer. The whole thing is squared, so be careful with your brackets. And we get an answer of negative 5 newtons. Nice and easy. And the way we interpret it then is that this means there is an attractive force of 5 newtons between these two things. Okay, so negative means attraction, positive means repulsion. So pretty straightforward. Okay, now hopefully not writing it hasn't thrown you too much. Remember, you can always pause it and copy down your working out as you go through. Go back and annotate it with stuff that I'm saying at the same time, just to help out. So let's have a look at a more complicated one. Here's a 2D system. So here's a multi-particle system on one dimension. A system of 3 charges in a line consists of objects A with charge of 10 microcoulombs, or positive 10 microcoulombs, B there in the middle with negative 10 microcoulombs, and C with positive 10 microcoulombs, separated by distances to their centres as shown in figure 7. So you can see here between A and B we have 100 centimetres or 1 metre. That's positive, that's negative, so they must be attracting. And here we have B and C 50 centimetres, and they must be attractive because again it is positive and negative. We're told here distances are measured at 2 significant figures, which probably should matter. I likely have not paid attention to it, in all honesty, which I really should. We want to calculate the net force on B due to both A and C. Okay, we've got 2 charges, we're going to have 2 forces, we need to calculate both force. So we need to calculate the force of A on B, and we need to calculate the force of C on B. Once we have those both, then we can look at the net force. So let's start with A on B. We're going to do the same thing. We're going to get our variables. We'll make A equal to big Q. So 10 times 10 to the negative 6, and so B must be the negative 10 times 10 to the negative 6. The radius here is just 1 metre, because it's 100 centimetres. And we need to work out the force. So I've done a little bit of complicated notation here. Force of electric, okay, or electric force, AB, so A onto B. Sometimes people use on different ones, like they'll go BA and say it's B from A. I always like to put the one that is doing it first and then the one that's receiving it second, because you're saying it's coming from here and going to here. It just reads a bit easier for me, but again, you can follow whatever convention you prefer. Let's write our formula. Same formula as last time. Let's make our substitutions. So we can see here, our big Q, 10 to the 10. Sorry, 10 times 10 to the negative 6. Our little one, negative 10. And we've got our 1 squared on the bottom. Pump it in, and we get that the answer is 0.9 newtons. When we think about it, it's B is getting pulled 0.9 newtons to the left, because A is to the left of B. Hopefully we can see that. Okay, let's work out the other one. Now, the charges are going to be the same. There's the same Q values. C here is also plus 10, but the distance is going to be different. So the force should be different. Okay, the distance is half. So our Q, our radius, our formula, and our unknown, our formula, our answer. And so we see here, even though it's only half the distance, the force is now 4 times bigger. Remember, that's the power of radius squared. So we have here that B is being pulled by 3.6 newtons to the right. Okay, so we can see here that the pull to the right is a bit stronger than the pull to the left. So our answer should be something to the right. Okay, now I have to wipe this off because I don't have enough working space. So here's our summary. We have our particle B has 0.9 pull to the left and a 3.6 pull to the right. Let's draw the arrows. Okay, there's our 0.9, there's our 3.6. Now, when we are looking at the sum of vectors acting on something, we draw them head to toe, and then the difference, from where we start to where we end, that is our net force. That should be our, when we draw it, that will be our net force. So here's my vector to the right, my big long one, my vector to the left. So the thing I'm trying to work out here is this difference. Okay, we can see it there in orange. The blue is a little bit pale and maybe might be a bit tricky to see. I do apologise. So let's put some numbers on there, and we can see that our F net will be 3.6 plus negative 0.9. Remember, it's going in a different direction. Okay, if we make 3.6 positive because it's going to the right, the negative must be to the left. We could do the other way, wouldn't matter, but we'd have to contextualise our answer. And so we can see here I've said the net force at the end will be 2.7 newtons to the right. Okay? If we establish that to the right on the picture was to the east, we could also say east. Okay? But we'd have to establish the direction somewhere, either by saying a positive and saying positive is to the right, but we have to establish it somewhere. Okay, now that's a fairly straightforward example. We just have to do the same thing twice and then look at what our results did and go back to thinking about just simple vector diagrams. So even though it's with how we're getting the force is new, once we've got the force, it's just back to trigonometry and we're about to deal with some triangles. Alright, we've got 3 different examples, and these ones starting a little bit more complicated now. So here's 6.1c, and we have a system of 3 charges. We've got A up here in the upper left, we have B up here in the upper right, and we have C here at the bottom. Okay? Now A and B are both positive 5 microcoulombs. C though is negative 5 microcoulombs. And the separation distances are on there. So AC is 5, BC is 5, so AC is 5 centimeters, the distance BC is 5 centimeters, and the distance between A and B is 7.1. Now, the distance between A and B won't matter for this one because we're looking at the force on object C, but we're going to use it for example D next. And they're told here that it makes a right-angled triangle, and the 2 interior angles, as said in the question, is 45 degrees. They mean these angles up in here. Okay. Again, we have to find out the force of A on C and B on C. Okay. And this time I'm just going to put up all our all our variables in our one step. So I'm going to let A be equal to big Q and C be equal to little q there. We have our distance of 5 times 10 to the negative 2. I could have used 0.05. It's up to you. And then our force, plug in our equation, we've got our answer. And we see that it's a pull of 90 newtons. So this one here is getting pulled up this way. And when we do B on C, we'll find it'll be the same thing because the numbers are exactly the same. So there must be the same answer. Pull of 90 newtons up this way. Let's draw what that looks like. Here is our C would be down here at the bottom, and we can see it's getting pulled at 90 newtons and 90 newtons. We're told that there is a 90 degree angle there, so this 90 degree angle carries over. Okay, I've also labelled the 45s on this picture now. Remember, we have to draw it head to toe, so let's draw it head to toe. 90 degrees. Now if this is 45 here, that must be 45 down there, so I've put my 45 down here. And the same thing here, if this is 45 up here, this must be 45 down here. So here's my second vector. Okay, so this is A to C, and this is B to C. Yeah, B to C up here. And now we need to find the result, which is going to be from start to end. Alright. Now the really good thing is we can see here that this is a right angled triangle, because if that's 45 degrees, that'll be 45, that'll be 45, and 45 plus 45 is 90 degrees. So we've got a nice, easy right angled triangle. Let's use Pythagoras to solve it. And we can see that our F net, okay, our orange line here, will be equal to 90 squared plus 90 squared, and we take the square root of it. Now if you have a bit of issue with that, come see me during lunchtime, because visualizing this might be a little bit annoying just because it's the perfect situation and you have to sort of understand your geometry a little bit there. And we get that F net is 127 newtons north. You could also say 127 newtons up the page, or upwards. Those would also be acceptable answers, because nothing here defines whether something is moving up and down in three-dimensional space or north, east, south, west. I'm just using north as the default. So this one's pretty easy. Okay, gets a bit more complicated, but we've got the same established start. Working out our forces, and then we construct a slightly more complicated vector diagram. We do head to toe, and then we recognize what's the best tool to use. In this case, it was a straightforward Pythagorean theorem for a squared plus b squared equals c squared. On to the next. Okay, same system, but now it wants to calculate the net force on B, this one up here, not this one down here where it's in the middle and they're both doing the same thing. B here we can see, well, there'd be an attractive force between these two because they're opposite charges, but there's going to be a repulsive force between these two because they are the same charge. Let's start off with what we already know. We already know the force between B and C. We worked it out in the previous one, so I'll just tap that out quickly. We wouldn't, if this was a sort of question on an exam, we wouldn't have to re-solve it. We could just say, oh yeah, this is what the force of B and C, we proved it earlier. Okay, on to A and B now, because we're going to need the force of A on B. Same process. Okay, now I've just gone straight to the formula. Let's have a look. We can see here's my charge, 5 times 10 to the negative 6, 5 times 10 to the negative 6. They're both in microcoulombs, and they are both positive 5. But here I've got a different distance, 7.1 centimeters, 7.1 times 10 to the negative 2, because here's the distance between my two charges, 7.1 times 10 to the negative 2. We slap it in, we're going to get a value of 44.6, which makes sense. The charges have the same magnitude, but they are further apart, so the force should be less. And I've also said here it's a push of 44.6. Now, this particle is just due west of it from the diagram. If those are both 45 degrees, we would assume that this thing is just a straight line, and so probably is going to line up with east, just because there's no references, so let's say that it will. So this is going to be pushing B off to this side. Let's see if we can do it. Pushing B off to this side, while C here is pulling it down this way. Let's draw that. Here's our summary. We've got a push of 44.6 newtons east, and we've got a pull of 90 newtons 45 degrees southwest. Okay, so here's B. We've got a push, and we've got a pull down this way. Alright, so we're going to do the same thing as before. We're going to draw them head to toe. We've got that 45 degree angle there as well. So here's my head to toe. Here is my resultant vector. Now, because I can see the working out in the textbook, I know that this is going to be slightly bigger than 90 degrees here. I would generally always draw my triangles as slightly bigger than 90 degrees as a just in case, and then never assume that you know that an internal angle will be 90 degrees unless you're very confident about your geometry. Let's label it. we've got our two vectors that we know, a 44.6 and a 90. We've got that angle there, which means that the inside angle here must also be 45 degrees. Okay, so if the outside is 45 degrees away from south, and the other one there was going due east, then it also must be 45 degrees away from that vector there. And we don't know our force net, and we don't know the angle. The question doesn't actually ask us to work out the angle, and it might be because it can be a little bit tricky to do. He does work out a different angle, the angle on the other side. If we continue that 44.6 on a straight line, he actually works out the complement here to theta that I've labelled. Alright, now we could use trigonometry, break down our 90 newtons southwest into a west part and a south part, and work out what the net result would be. However, you can use, I'm going to do that in the next one as an to show you, but we're going to do this one by the law of cosines. So in year 10 you learnt the law of cosines, and the law of cosines says for any triangle, a squared equals b squared plus c squared minus 2ab cos a. Now it doesn't matter what sides you choose for a squared, b squared and c squared, except the angle that's going to feed into your cos must be opposite the side that you have there for that's wrong. Sorry, that should read BC cos theta. Let's see what's the quickest way to fix that. The same copy paste formula up here. There we go. So that's what happens when you start rearranging your Pythagoras, because I'm so used to a squared plus b squared equals c squared, and the first time I learnt this formula I had c squared equals a squared plus b squared minus the rest of it. So you've got your 2bc, those are the sides that you know, or any of the sides on there really, doesn't matter which, but your angle cos a must be opposite your a squared. So here we've got 45 degrees, we know that one, so that's going to be my cos a. We're going to have to use that one, and that's going to have to be my a squared, my force net. Okay, so let's chuck that in and we see what we're going to get out of it. Okay, so our F net, we don't know what that is, and note that's F net squared, but the equation editor does some weird stuff there, equals 44.6 squared plus 90 squared, take away 2 times 44.6 times 90 times the cosine of 45. Okay, so we're using all three sides, and we're using the angle that is opposite the unknown side. Most of the time that'll work out quite nicely. Sometimes it won't, and you won't have the angle opposite the unknown side like this, and you'll have like a b squared and a b, in which case you just solve as per usual, and you'll end up with a quadratic, and you'll get your two answers out of it. One of them will make sense, and the other won't, and you just choose from there. And so let's plug that in, and we're going to get an answer of 66.4 newtons. Okay, nice and straightforward there. So the net force, most of this 44.6 gets cancelled out. There's only a very small amount going past it, and so most of it is just some value going down. But what about the angle? Now I'm going to use the cosine rule again to work out the angle. Now that I know all three sides, I can use this 90 newtons opposite theta to work out the angle. And some of you might be going, but there's an easier formula, and we'll get to that in a second. So again, same formula, but this time my A is going to be the 90. It is opposite the theta. So 90 squared equals 44.6 plus 66.4. Those two don't matter. whether you use, we could have swapped them around because it'd be the same answer, because again, a times b equals b times a, and here we've got a plus b equals b plus a, even though they're squared, it's still the same thing. Take away 2 times 44.6 times 66.4, the symmetry there is just a coincidence, times the cosine of theta. Now, when we rearrange that, this stuff here, this 90 take away 44.6 squared, sorry, 90 squared take away 44.6 squared take away 66.4 squared will be a positive number, and you'll end up dividing by -2. It's okay, your calculator can handle a cosine of a negative value and still give you the right answer. And we plug that all in, and we will get that theta equals 106.7 degrees. So, which matches what we see visually, but in this case, it was just because I knew what it would be that I knew it had to be bigger than 90 degrees. Now, some of you may have been going, but what about the sine rule? Okay, well, let's do the sine rule. The sine rule says that the sine of an angle divided by the any side is equal to the sine of the angle divided by that side. Now, you can flip this the other way around. In fact, a lot of texts do. They have the side divided by the sine of the angle, but they're just ratios. It doesn't matter what order you put, whether you do it this way or you do it the other way. So let's see. We're trying to work out theta. So our a has to be 90, and our sine theta will be, or sine of a will be theta. And we've got 45, so we have to use f net and 45. So let's substitute that in. Okay, well, I've done it for b, but it's the same thing. So sine of 45 over 66.4, which we just worked out, equals sine of theta over 90, which equals 73. They don't match up, so it can't work. Math's wrong. It's all proven wrong. Oh God. Now look, here's the thing. Because sine gives you two solutions for different ratio, there are two different ratios that produce the same solution. You see here that 73.3 and 106.7 are complements of each other. They add to 180 degrees. So sometimes you've got to be careful. Like I did this first, and I was sitting there going, this isn't the right angle. I can see it's too small. And so I went and checked with the cosine rule, and it was simply because it was one of those weird angles where you end up getting two possible solutions. So sometimes you're just going to have to check, and it's not great. So that's not the answer. Let's put the answer in words now. So we have a net force here of 66.4 newtons, and we can see here that this is 106 degrees from east all the way past. Well, 90 degrees would take us south. I've made a mistake there. That should read south, 16.7 degrees west. Okay, so make sure that you fix that up in your books if you're copying down this solution here, because this is a little bit to the west of our south here. Again, there is no cardinal directions referenced on this. I'm just assuming that down the page is south. You could also write this as 16.7 degrees left of down the page, and would still be marked correct. Okay, so you just have to give some sort of reference for your directions. Okay, last example. So we've seen two ways of doing 2D things. One is simple Pythagoras if you're lucky. Then you've got the cosine and sine rules of triangles, but again, sometimes they will be cranky. This is the one true only way that will always work. You don't have to be clever with geometry, but it is slower. Okay, here we've got three charges. We want to work out the magnitude and the force, magnitude and the direction of the force on charge C. This little guy down the bottom. Each charge is positive 4 times 10 to the negative 8 coulombs, and they are arranged in an equilateral triangle that tells us that the internal angles will be 60 degrees, each with a side of 20 centimeters. Okay. Again, we've got two charges acting on C, but what we can clue in here, and we're going to cheat a little bit, is that A and B have the same charge. They're both 4 times 10 to the negative 8, and they've got the same distance. They're both 20 centimeters away. Therefore, the magnitude of their charge should be the same. Okay, think on that for a second. If they're the same charge and they're the same distance, the force will be the same. The direction won't be the same, but the size of the force will be the same. So I'm going to state that. Size of force of A on C will equal the size of force of B on C. And that way we only have to do our force calculation once. Okay, once is better than twice. Going to do the same thing. Here's our values. Big Q, little q, same charge in this case, so it doesn't matter which one we gave to what. And our radius is 20 centimeters or 0.2 meters. Chuck it in our equation, get an answer, and it must be a push of 3.6 times 10 to the negative 4 neutrons. Okay, so it does say neutrons, newtons. Let's draw that out. Now, I've drawn my vector, and the angle we know is 60 degrees from our diagram. So let's put that in. And I'm going to break this down into its constituent parts. It's bit going to the left, it's bits going to the right, it's bits going up, and it's bits going down. We're going to go back to Year 9 trigonometry. Okay, Year 9 trigonometry will always work. Sometimes it might be a little bit slower, but it will always work. So I'm going to need to work out, well, what is my force of A on C in the x direction, and what is my force of A on C in the y direction. Okay, we can see our nice right angle triangle there. So our x value is adjacent to the 60, so that's going to be the cosine. So our force x is going to be equal to 3.6 times 10 to the negative 4, there's our hypotenuse, times the cosine of 60, which solves as being 1.8 times 10 to the 4. And I'm going to put it in language, 1.8 times 10 to the 4 to the right. Now let's do y, we do the same thing. It's going to be sine though instead of cos because it's opposite. We get our value down. Now, we've clued in a bit here that, you know, A on C and B on C are going to be the same, except the direction should be flipped. So I'm going to take the triangle and draw it again. But you can see here I've just flipped it around. We see that BC in the x direction will be cosine, and BC in the y direction will be the sine of the angle. So here's our f of x to the left. Now that's important, so we've got a left and a right. We're going to come back to that in a second. Now let's do our y values. And we see, hey, it's the same thing. It's also 3.12 down. Okay, I have to wipe the working space. So here's our summary. In our f of x, we found two things. A was acting to the right, and B was acting to the left. Well, they're the same size, and they're in opposite directions. So our f of x, our net f of x, just must be 0, because they cancel each other out. So we don't need to worry about them now. Our y values, though, they're both acting down. So let's add them together. Okay, the net will just be add them, and we get a total of 6.24 down the page, and we're finished. Now if we had some value of the x direction, we would end up going, well, we're going to have to add them back together using Pythagoras' theorem to work out the size of the force, but that would just be one more step, and then use tan to work out the angle, so 2 more steps. But this will always work if you are uncertain about any of the others. So if you were looking at cosine of triangles and going, nah, use Pythagoras, okay? Use your trigonometry, keep it simple. Okay? You do not get extra marks in senior physics for using more complicated math. Sometimes it can be faster, like I can probably do it with the complicated math faster than you guys can do it with the complicated math. I can likely do it with complicated math faster than you can do it with simple math. I could probably do it faster with simple math than you do with complicated math, and that's just familiarity. But at the end of the day, if you practice over and over with what you feel confident with, you will find on the exam that you will have plenty of time to knock it out and get through it. It's if you are not confident with the math and you are over it that you'll find difficult to get through. Okay, so that's the last example on this one. Let's head on. So our lesson summary, we've done a couple of things. We have looked at the equation for electrostatic force between particles, and we've seen how to apply forces and calculate net forces in 1D and 2D situations. Okay, remember they're called vectors. Now, for your entrance slip, please have a look at chapter 6.1. Remember, we're in book 2, not book 1, book 2. If you go to book 1, 6.1 is something to do with linear motion, as I believe. And complete questions 1 to 9 in chapter 6.1. copy those answers into the 4.1.1 space on eLearn. Thank you very much for listening, guys. This was a long video. Have a good night.